Hey everyone, sorry I'm a minute or two late. Yep, so let me share my screen. So today's notebook, the link is in the chat again. This is again a cleaned up version of the notebook that we were using yesterday. And there is one additional cell at the bottom, which basically describes what we have to do today. So please have it open in Google Colab, and we will also allow others to join, and then we'll start in a minute or two. Right. So I have my copy open. I'm going to execute all the cells that we have already implemented. So that will be till the very end of the notebook. So let me execute everything. Then I will do a short recap of what we did yesterday. Uh, then then we will see what exactly we want to do today. And there are two things that we want to do today. There are a few algorithms that we want to implement, and after that, so there's no starter code for the algorithms today. I want everyone to be able to read through. There is a small couple of paragraphs on these two algorithms that we would like everyone to read through, and then implement the two algorithms and see if we can tweak the parameters and get good results. And then toward the end of the session, uh, I'll just give an introduction to what our project is about, the take home project that everyone is supposed to submit uh, at the end of this course. So that is sort of the agenda for today. Again, if you have the notebook open, then please run through all the cells, make sure you execute all of them. And it is taking a little bit of time to execute. but in yesterday's class we had implemented constant alpha. So yep, this seems done. Right. So the last thing we did was we were trying constant alpha with different parameters, and I hope everyone was able to play around with the parameters. Is the audio still low?
No, it's fine.
Can you hear me now? Is the audio level, the volume is fine, or does it seem?
Yeah, it is better than earlier, but still not very clear.
Okay. Does it seem totally fine now?
Yeah, it's fine now.
All right. Do let me know if the audio gets faint or if there is any other issue. So basically, what we did yesterday was the last thing we did was implement this concept of constant alpha, a constant learning rate, where we are no more dividing by the number of visits for every state action pair. Right? We implemented this, and then I was expecting everyone to sort of toy or experiment with the different parameters. So we had number of episodes, we had a starting value of epsilon, which we typically didn't want to change. So the starting value was one, which ensured that in the beginning you were purely uniformly random. You were selecting uh, every action uniformly with the same probability in the beginning. The parameters that we wanted to tweak was the number of episodes, the minimum value to which you want to bring down epsilon to, which we had set to zero point 0.1, the epsilon decay factor, which sort of controlled how much epsilon reduced every episode, and the learning rate over here, which we were calling alpha, right? Uh, so this is something that we still need to do. It will take some time. The values that I have set here based on a little bit of experimentation, they seem to get me good results most of the times. It won't return the same policy, of course, because it is based on exploration, and sometimes because of the randomness, some few things go wrong, and you may not get the exact same results every time. But for example, in this execution, in this run, I'm getting a perfect policy, right? So the question for today is, again, there are things that can be optimized here, that can be tuned here, but that is something that everyone has to sort of experiment with and find out. So really, what is the impact of episodes and epsilon and decay and everything? And I gave a few pointers to how to do that. So one thing is you want to plot the value of epsilon, so how fast it is decaying, how many episodes does epsilon take to decay, and then you can sort of measure how quickly or how far your algorithm is actually learning by plotting the delta. So if you remember, when we were trying the dynamic approach, dynamic programming based approach, we were taking the delta of the 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 returns table before and after, updating the table. So we can do that here as well. Take the delta, that should be a single number, and plot it against your episodes and see how many episodes are really needed. Right. So maybe I have set the episodes to 5,000 here, but maybe after 2,000 episodes, the algorithm isn't really learning anything. So I can either cut down to 2,000 if I'm fine with the end result, or I can tweak other parameters so that it can go on learning for the remaining 3,000 episodes between 2,000 and 5,000. So that those are some of the pointers we can try out. The thing that we want to talk about today is how can we get faster convergence, right? So we have already been making incremental changes. One of the reasons we sort of introduced constant alpha was because we wanted to speed up things, right? And with an update like this one where you were dividing by the visit count, which we were doing previously, so in that case we talked about how the visit count, the division, basically slows down the update. As the number of episodes increases, as the number of visits to a state and action pair increases, the update gets slowed down. So this was one change we made to speed up things and get faster convergence. And now we want to explore two well-known algorithms that generally get much faster convergence than the approaches we have seen so far, right? So what we are going to do today is open this link, and when you click here, should it should take you to this page, which is really one long article on reinforcement learning, but we are just going to focus on two sections over here. So one says SARSA on policy TD control. I'm going to explain these things. Uh, the other one says Q learning off policy and TD control, right? These are similar to the algorithms that we have implemented yesterday, but then what I want everyone is to just go through these two. I'll come back to explaining what on policy is and why is it called TD control. But first of all, if you can go read these two descriptions and see if this makes a little bit of sense or not. Are you able to tell how these algorithms are different from what we have been doing so far? That is the first thing I want everyone to do. So let's pause for like 10 minutes and really look at these two algorithms very closely. And before we do that, uh, there is a little bit of notational difference over here. So they should be easy to understand, but I still want to everyone should understand that the Q being used over here is just the returns table. So we haven't really tried to teach ourselves the notation and the exact terminology, all of it. We will do that in the coming weeks. But Q here is the returns table, right? So you can sort of make that out by looking at this equation, that okay, this sort of corresponds to the equation that the update equation that we have been using so far. Q is your returns table basically, and R over here is the immediate reward. Other than that, S of course is the state, A is the action, so there is no additional new notation, right? So now I will stop for some time, and please go open this link, read through the description. I would say read SARSA first and see if you can understand what is like the biggest difference between SARSA and what we had implemented with uh, in the last step yesterday. Cool. So I'll pause for a while, like 10 minutes, and if you have questions, keep them coming, post them on the chat or unmute yourself and ask me. But take a close look at what they're describing here. is what do you think is the key difference if you compare this algorithm, for example, SARSA, to the algorithm that we implemented yesterday, this code over here? What is that key difference between this implementation and this pseudocode? Of course, the two are fundamentally different algorithms, so we are trying to understand what that key difference is. And as a hint, we just need to, like, there is other information as well, but if we just look at the update equation, how does it seem different from the update equation that we used yesterday? This is our update equation, right? Over here, this is our update equation.
Uh, we are using next state estimate to update estimate of the current state.
Yeah, right. So that's right. If you look here, if you were to copy this over and compare to side by side, then this is same. We are just calling it estimated table, estimated returns, and they're calling it q. This is same. Again, on the right hand side, we can rewrite this equation. We can remove this plus over here. We can bring this here and put the plus over here, right? So this is sort of q of sa in their notation. This is again q of sa, q of stat, which is the current state and the current action, which is the state action pair that you want to fill up in the table, right? So this matches up. Then alpha is of course there, the learning rate is there. Then we have rt plus 1, uh, which is in there. So we basically want to compare what is inside this pair of parentheses. uh, this is again q of sa, the last term, which matches up with what you have here, right? So q of stat is appearing in three places: on the left hand side, then over here, and then within the bracket. What is different is that over here we are using return, which we previously computed by running an entire episode, and then for every state action pair we computed the return corresponding to that episode. Over here, what we are using is the immediate reward, which is rt plus 1. You can call it rt plus 1 or rt, that depends on your notation, but in the reference book they use rt plus 1. So this is the reward that you get when you go from state t to state t plus 1, right? So this is the reward part, and then this is the return value of the next state for some other action at plus 1, right? And this is where they are talking about how to get that action at plus 1, right? So this is the key difference, and this is a lot more like what we were doing with the dynamic programming based approach. If you remember the last implementation we had of the dynamic programming, we were basically finding the return value for a state action pair in terms of its immediate next state and action, right? So we had a max over here. The max isn't here, but this is very much similar to the dynamic programming approach. Now, why this is needed, why we are talking about, is first of all, what is TD control? So TD is an abbreviation for temporal difference, which means difference over time. And the idea is that this implementation over here, so we spend a substantial amount of time generating an episode, then updating the table, then you generate another episode, then update the table again, right? So we can perhaps speed this up if we update the table every time we generate a step. So don't wait for an entire episode to be generated. With every step you are getting some additional information. Every step tells you what the reward was, what the next state was, and what was the action that you took. So just use that information and update the table immediately. That is the first idea. But when you sit down and try to implement that, then there is immediately a problem, because if you're not executing the entire episode, if you just take one step, then you cannot compute the return for the for any of the states, right? So because returns requires you to reach the terminal state, and that is how we were computing returns, right? And that is where we go back, sort of fall back on the older idea that okay, we will just use whatever return is there in the table. If we cannot compute the return afresh, then let us just use the return in the table. Okay. uh, Specifically we want the return for the next state, right? Because that is what the equation was. If you go back and look at the recursive equation which we have adopted, so these were the values. In this case we were taking the maximum over here, because we were directly trying to use dynamic programming. But then when we move to a sampling based approach, so we are not taking max or anything, but we do want an estimate of the return for the next state, and for some action t plus one, right? And that some action at plus one, in the case of SARSA, that action is again picked using the greedy policy, right? So if you look at this step over here, then it is basically, there is a little bit of confusion, but this should ideally be arg greedy max, right? So it's not a simple arg max, but generally this is arg greedy max. So a combination of uh, exploration and exploitation, right? So if you combine both the ideas, then it's very simple. You are in some state, you decide to take an action that is based on the greedy policy, right? The epsilon greedy policy, sorry. So we take that action. Let's call the state s0 and the action a0. So in state a0 s0, you take action a0, and now you want to update the table, right? So the first thing we get from taking action a0 is that now we are in some other state s1, and we have some reward r, right? But then when we want to use this equation to update things, then we need an estimate of the return, right? And to get that estimate, what we can do is we can add up the immediate reward that we already got by executing a0, and then we can get another estimate of the return that you can get for st plus 1, the new state. And to do that, you again pick another action. This is what SARSA is doing, right? So you again pick that action. How do you pick that action? Again, using the same approach that we were using for picking the previous action a0, which is just go to your table, combine the table with some randomness, and pick it epsilon greedily, right? So pick some action at plus 1. And once you have S0, A0, and S1, A1, what they are calling at ST, AT, and ST plus 1, AT plus 1, then you can use this these two terms. This is an approximation of, another updated approximation of the same thing, right? So QSTAT is one approximation which is built from many episodes, but then we also wanted another new approximation, and that new approximation is new because this reward is something that you have just learned from the simulation, right? So RT plus one has definitely updated. This is going to come from the policy that you are going to use. We are currently using an epsilon greedy policy, so this Q value will still come from the table and a combination of epsilon greedy policy, but this has definitely updated the reward, right? Uh, so does this make sense? Is there any confusion? Anything that is not clear? If you don't want to roll out an entire episode, just take one step, and then from that one step try to find out what would be the return for the starting state. And to do so, take the immediate reward and then take the return in the next state. But when we talk about the return from the next state, we have to specify with corresponding to which action, right? Earlier in the dynamic programming based approach, we were just taking the maximum return. In this case, we are applying the same approach, which is a combination of exploration and exploitation. So we say, okay, let us try another step in the new state, and whatever return we'll get from it, we'll use that as an approximation of the return that you can get from st plus 1.
One question here. So RT plus 1 is constant given action, right? Always.
Yeah,
That is as per the rule of the game, right?
right.
So compared to this one and what we have implemented, right? As you mentioned, the RT plus 1 is only delta, and that is a constant which we are adding every time as per the alpha.
Right.
So how much it will impact the overall, return? Like, it's a
Yes.
fixed alpha into reward.
Right.
It is not changing.
Yeah, but then this part is also going to change. It will change sometime later in the loop, because there is a top level loop, then there is another loop behind that, which is basically generating an episode. So this value does change, but in one iteration, in one step, we are sort of holding it constant. So if the update is not only depending on the reward, but this value as well, which is going to change as the training goes along.
Okay.
Right.
Uh,
In this step, of course, it is constant, but sometime later when you reach this state and this action, then of course this value will also get updated, and then when later you, if you ever come to this state, then of course that updated value get used.
so Farhan, so we are using alpha into gamma of the next state return, right? So that means it will be very minimal. That is to make sure that we are not getting influenced by any bad, action that is taking place in the next step.
Yeah, so this actually automatically comes from the equation that we sort of saw earlier, which was, if you want to find the return of a state stat, right, you just if you want to find that in terms of the return of st plus 1 and at plus 1, then you need to take the immediate reward, that the reward that you get from st to st plus 1, and then you need to take the return for st plus 1 and at plus 1 and multiply that by gamma, right? Because this is how the return shifts, because this has to be multiplied by gamma to get the return for stat.
Yeah.
We sort of saw this, I think, 2 sessions back when we were trying to implement the recursive algorithm, right? I can, if there is confusion, I can open that older notebook where we had the equation. So as you move from one step to the next step, the gamma also shifts. So if you have the return for for the next state, then you can get the return for the previous step by multiplying it by gamma,
Yeah, discounted return.
right? So that is automatically getting from there, right? So let us do one thing, which is this could still be confusing, and maybe feels like a lot of change uh, very quickly. So let us try to convert this into code, right? What you could do is just go back, copy over this code in a new cell, and there are going to be changes. So copy over this code and then refer to this algorithm, the SARSA algorithm, and then change your code. And the change, like I said, is this line is definitely going to change, because over here we were just generating the entire episode in one go. Now we don't want to do that. We do want to generate episodes, but one step at a time. And there will be a difference, because now between any 2 steps the table is going to get changed, right? So at every step of the episode you are updating the table. So when you generate the next step, that may be different from if you had just generated all the n steps of the episode in one go. So let's try to implement this, and this is going to take time. So we will go to breakout rooms for some time and implement this, and if you get this right, then this should converge, this should give you a good policy. uh, Let me open the breakout rooms. Okay, so I have opened the breakout rooms. You can talk to others. You can try writing code. I will drop in to see how is it going, and I'm also going to share another link which will perhaps give you a better understanding of what it means in terms of the algorithm, because this is pseudocode. Then translating this into proper code could be a little confusing. Okay, so we're back, and I would like to try to explain my solution. I think everyone gave it a shot. Again, you would have to experiment with things, write the code yourself to really understand the algorithm. But since this is very close to what we did earlier, I think it should just a code walkthrough should also make sense. So this is my code. And first of all, SARSA is really an abbreviation for state, action, reward, next state, and action. So this is exactly what we are doing in this algorithm, right? So I copied over the code and then made a few changes. So the return table is still being constructed in a similar fashion. There is no change. I left the hyperparameters unchanged, so episode and everything is unchanged, right? Uh, Over here, I have imported and used a module TQDM, which is just to print a progress bar. I'll come back to that a little bit later. But if you look at the core logic, so this is our top loop, which was going, for a number of episodes. So again, episode is 1,000, so this will execute for 1,000 times, right? The first thing that I'm doing within that episode is generating our starting state, which will always be the reset state or the initial state. So I do that by calling foosball or reset. Sorry, this is of course this has to happen at the beginning of any episode, so there's nothing new here. The change that happens is that now I need an action to take in this state. Earlier, I had a function that I was calling, and that was doing this. But now I don't want to generate an entire episode, right? We had this function earlier, generate epsilon greedy episode, right? Sorry, yeah. This we had written this function that gave us an entire episode using the epsilon greedy approach, right? But now we don't need an entire episode in one go. We instead want to generate one step at a time, then we will generate the next step. And that also becomes essential because we are updating the table in between two steps. So if you generate the entire episode at the beginning right over here, then that episode, the states and actions in those the states particularly in that episode are going to come from a stale version of the table. We don't want to do that. So I just generate this logic over here. This is just copied from inside the function that we created earlier. So there are action and action probabilities, and then I'm sampling one of the actions using an epsilon greedy approach, and I'm calling that action A0. So it's like easier to map this to the algorithm that we saw over here. Right. So this is my beginning state and beginning action. I clear the done flag. I recompute epsilon, and then this is sort of the loop that runs over one episode. So this will keep running until you reach the end of the episode, right? And you might want to have a while loop here. You might want to have a for loop with some maximum episode length, just to make sure that you don't get stuck anywhere. But this is the loop that sits inside the top level loop. Now over here, of course, I need a next state. So I'm going to call foosball.step. This was again happening earlier, but it was happening inside another function. I feed it this action. So I get the next state, reward, and the done flag. Now what I really need to do is, because I need the return value for this state, the new state. I need some action for this state, right? So I need to pick one of the four: north, south, and east and west. And what is done in SARSA is that you again pick the action using the same technique or using the same algorithm, which is the epsilon greedy approach. So this is exactly this code, and these four lines are the same. The only thing that changes is that now we have S1 over here instead of S0, which we had over here, right? So this should ideally be refactored out into another function, but just for the sake of clarity right now, there is this repetition. So out I get A1, which is our new action, and that is all the information we need. We already had state 0. We had already picked an action in state 0, which we called A0. Then we had S1, the reward, and that is everything we need. And now look at this equation, which is updating the table. So we go to S0 and A0, and we want to add something to its current value. And that something is based on the reward I got from taking this step. and then gamma times the return of the next state. So this has to be corrected. This has to be S1 and A1. Right. This is exactly the equation that I sort of wrote over here, right, when I was trying to explain things. So this is that equation. So this is the reward plus the return for the next state. This is again an estimate. This entire thing is a new estimate uh, for this value, right? So this is sort of our new estimate of the return. This is our old estimate. We are taking the difference, then multiplying that by the learning rate, and that's how we are updating the table. Now this is just one step, not an entire episode, just one step, and you updated the table, right? And right after we have executed this step, my S0 and A0, I'm just updating them because now my S1 and A1, they become S0 and A0 for the next iteration of this loop, right? And epsilon decay, that is being done outside the loop, obviously because we want to decay epsilon at after every episode, not after every action. That would be too quick. So this is essentially everything. If you look at this algorithm, what this says versus the implementation here, this is like a verbatim implementation. And if you run this, so because we are using TQDM, we also get this normally doesn't happen. Normally you would see a progress bar on a single line. This is happening because I interrupted the control the flow earlier. But you could see that in just 8 seconds it was able to get 100%, which is we set the number of episodes to 1000 over here, so it shouldn't take much time. uh, you also get the number of iterations over here. This will be something useful when we are building the project and otherwise too, because as the algorithm is learning, you would expect it to uh, go from the starting state to the goal state much faster. It would take more efficient routes, right? And that would mean that this inner loop, this should get with over time this should get faster and faster, because now most of the time you would be taking shorter routes, except when you take a random action or a bad action. So you would generally see a trend where the number of iteration increases, right? So it started at 97 something, and then it goes oscillates a little bit, but then towards the end it is like 116 or something, right? So you would generally see this trend. Now I have executed this, and I just need to look at the policy, right? Again, this is not a perfect policy, and if I were to run this again, probably I will again get a policy which had issues. But this is sort of looking okayish. This is not perfect, but looking okayish, and we can go back and we can tune these parameters, because I just copied them over from the last case where we were learning things you know one episode at a time. So one thing we were discussing is perhaps we need to decrease alpha, because if alpha is too large and you are now making updates every step, then you might make a bad take a bad step and make a bad but large update, and that will last in the table for a long time. So perhaps you need to decrease alpha. Epsilon, again, you will have to tweak by doing experimentation. Number of episodes, again, you will have to look at convergence and decide how many episodes you want to go. Uh, but this is the rough idea, and this is generally this should converge faster than an episode based approach, because now after every step you update the table, so the next step has got better information, and the next one has got even better information. So you're basically, if you used to have like 50 steps in an episode, now you are typically learning 50 times faster, so it should take you less number of iterations, right? uh, Again, you must change the parameters over here, and then run this again and again, and do the debugging stuff and figure out what are the parameters which, even if they don't guarantee you, they get you the right policy most of the time, right? That is super important. Is there any confusion, anything that didn't make sense with respect to the code or the algorithm? Right, and this will look very neat. This is actually included in the solution notebook, so if you open that up and look at the solution notebook, that is a more cleaner implementation, because this whole code has been sort of refactored out, so it pretty much looks like the pseudocode over here, right? So there's S0 and then A0 generation, and then there's S1 and A1, and then table update. That is all we are doing. Okay, if there is any confusion, do let me know. Otherwise, what we can do is try to attempt this other implementation, which they are calling off policy TD control. Again, TD is temporal difference. Temporal difference, because now we are just using the one time step to estimate the return for a state, right? And Q learning looks so much like SARSA. It is very like, again, the key idea is same, which we have been implementing over the last few sessions. So all the key ideas are same. The difference is how you get this estimate over here, right? So how do you get the estimated return for the next state? That differs, and that is sort of the only difference between Q learning and SARSA. So let's try to implement that. Mm, Again, we're going to take like 10 or 15 minutes. Go to breakout rooms, try to implement this, and tweak the parameters and see if you get the results. Okay, so I hope everyone tried to implement it. I'm going to show you what how I went about implementing it. So I'm basically trying to show you a diff of what has changed, right? So on the left, we have SARSA that we implemented previously, and then on the right is Q learning, right? So what happened? What was happening in SARSA was before you started a loop, you had a starting point which was uh, a state and an action, S0 and A0. And then inside the loop, we were computing S1 and A1 and using them to update the table, right? And then at the end, we were sort of setting S0 and A0 to S1 and A1 so that the loop can go on. In Q learning, you can really bring this part inside the loop. So you start with a starting state, then you just need to generate one action corresponding to that state. So A0 over here is being computed based on S0. So the logic is still same. Use S0 to epsilon greedily generate an action, which we are calling A0. And then this step is again same. We are going to uh, generate one step, and that is our S1 and reward and done, right? So this step S1 reward done is over here. Um, of course, update is the part where things change. So this part over here, this has changed now because now in state S1 we aren't really trying to find another action, right? This is the difference between SARSA and Q learning if you look at the algorithm. So in Q learning, you just pick the maximum, like you do with a greedy policy. So just pick the maximum and use that as an estimate of the return, right? In SARSA, we were picking a random action or an epsilon greedy random action. In Q learning, you do that with the maximum. So you don't need an action A1 over here, and the rest of the update equation is same. And of course, after you are done with the update, you only now need to set S0 back to S1. There is no other change in terms of the results. I have tweaked a few things. I changed the parameters looking at my solution, but with like 2000 episodes and an epsilon and an alpha, corresponding to these values, I get a policy that looks like this. Right? I can try running it a few times. And again, the choice of the parameters is by no mean the most optimal one. This is something that has to be done on experimentation. This is already done on a little bit of experimentation, but the more debugging you do, the more parameters you plot, the more you analyze when the algorithm is learning and how fast it is learning, uh, the better those parameters will be for you, right? So this is 2000 episodes. It seems to converge to the right policy most of the times. Compare this with where we were yesterday. So we were using 5000 episodes, and that was sort of giving us convergence. Few states were not getting the right policy, but we were still close, right? So first of all, the number of episodes is more. Again, we cannot be 100% sure that 5000 episodes is what we need over here or 2000 is what we need there. We need to plot the the delta in the table and see how fast that is converging, and you will see that it maxes out very quickly. So if we are doing it at least in the next case, in the case of temporal difference learning, you'll see that there is a very steep learning curve in the beginning, and then it sort of becomes saturated, right? So perhaps you can cut off even before 2000 steps. Maybe 500 is enough. So the first step is of course to find out the right number of episodes, but generally the episodes for this case is going to be much more than the number of episodes over here. The other thing is that even if episodes are similar, you could actually be saving time because not all episodes are equal. Over here we had an episode length of 20 set, I think. Yep, we were using a maximum episode length of 20. We don't know, we aren't doing any such thing over here. we can do that here. But if you compare the actual episode length, right, just keep track of how many steps it takes this loop to end, right? And this we know, because this is a small problem, we know that ideally there should be 5 or 6 steps, right? So if you keep track of that, or alternatively you can keep track of the number of iterations that you are doing here, or the total amount of time that is taking for this algorithm to converge, then you can do an apples to apple comparison between this approach and the previous one. And generally this approach would be faster because of the reasons that we discussed, right? So SARSA and Q-learning, they are very established, well-known algorithms that everyone is taught when they are getting used to reinforcement learning. We have taken a programmatic approach. We started with dynamic programming that didn't quite work. We made a few changes, made it iterative. We will sort of summarize that at the beginning of the next week in the office hours. But right now, if you have toyed with these two examples and the previous ones, you should have a good understanding of what the parameters are, what the algorithms are doing, right? And so it's a good time now to start thinking about the project that we are going to do, right? And that is what I sort of want to do in the remaining time. So the take-home project for this course is the taxi V3 problem, right? This is from OpenAI. There's a description of where actually it comes from. That is a research paper. They also link you to the GitHub code, right? And this is the first thing that we are interested in. So even before we go back to the description and, you know, or we can start with the description, but even before we start thinking about algorithms and parameters and solutions, we need to understand the problem. And to do that, we need to look at the code for the taxi environment. This is going to look a little different. The general design is similar, so the APIs will look similar. If you're going to use taxi environment, you'll see that basically you are again using the step and the reset APIs, but the implementation is quite a bit different, right? So we had a simple, because we had just in notebook we dumped everything into one class that we were calling foosball. Our taxi environment is built upon some other existing classes that OpenAI built, so that you can build more environments on top of them. So the idea is first to understand what the problem is and how the code is structured, right? So we will be looking at the taxi environment. We'll look at the discrete environment, this class that the taxi environment uses, because if you look at very quickly at this environment, you won't find any step function or reset function here. Those functions are actually coming from the base environment, the base class, which is discrete environment, right? So we need to be looking at these two pieces of code, understand how this is structured, read the description. The description is short description is over here, but you can also open this paper, and in section 3 of the paper there is like 3 paragraphs that sort of describe what taxi does. But that won't be enough. What we actually want to do is explore the environment and interact with it manually for some time, right? That is super important. So just write a little bit of code like what we did with the foosball environment, create an object, and then step for a few time steps and see if you understand what is going on, right? That is sort of step one. Then we will once you understand the problem, then of course we will have around 2 weeks time, so the entire next week, uh, which is week 4, and then one additional week after that, you will have time to solve this problem and submit a solution. But between now and Monday is a good time. If you have understood the algorithms that we are using and how we have built our own environment, then now is a good time to go and look at the gym environment. And this is one of the simplest problems that the gym environment has. If you look at the list of environments that they have got, uh, so there are all sorts of problems. We are right here in the toy text section. These are problems which are easy because they are just discrete, they are small, and they are also text based. So you can just print the environment wherever you like. You don't have to think of having some sort of a display where you can render a complex scene. These are all text based, right? So this is where taxi v3 comes from. There are a few other problems, but they are relatively more complex, because for example in some cases there will be stochasticity. For example, frozen lake, I think. So if you take actions in frozen lake, those actions are not perfect. If you want to go left, you might end up going straight ahead, or going even veering off right, because it's an environment where there is stochasticity, uncertainty. That is something we will be doing to our environment in the next week. But based on what we have done so far, this is the best project, right? So look at the code, look at the problem, try to understand this. And one thing we discussed in the first session was that if you want to work on a more challenging problem, that should be okay. So this is a project, we have to submit this anyway. But then if we have time left, and if you want to attempt something more complex, something more interesting, we can decide that. That could be one of these environments, it could be another environment, or your own problem, whatever it is. But the first requirement is of course to submit this to complete the course, right? uh, there are a bunch of other algorithm environments which are interesting, but the issues are that number one, you need a system where you can render them. So it's not going to work so well in the cloud. You need to have an offline setup on your laptop. They will also of course take a lot more time to train. uh, and they might have dependencies as well. For example, the robotics environments are based on other physics engines that you will have to install, sometime build on your system. That is why sort of we decided on this environment for the course. But it's okay to, if you have done the course project, then it's okay to pick up another problem and work on it on your system and set up everything, because that is also part of the learning process. So that is sort of about the project. I will introduce you to the project requirements. There's a rubric with 5 points in terms of what is needed. But really the first and second point in that rubric is about having a very good understanding of what you are dealing with, what the taxi problem is. And although on the surface this looks like, okay, this is a toy problem, once you interact with the environment, and once you start building your algorithms, and then tuning them and debugging them, uh, what we saw in the previous cohort was that there were some very good insights about what the environment is versus what we might think just by reading the description. So there are very subtle differences, lots of them, that different learners were able to find out only because they wrote the code, it didn't work, they tried something else, and so through that experimentation they were able to figure that out, right? uh, but in terms of preparedness, we have everything that we need to attempt this project. These are the algorithms that I would recommend. You can either pick SARSA or Q-learning and just write some code to for the taxi environment. The other sort of difference between what we have done right now and taxi environment is it's the number of states and what those states represent, right? In our case, it's very simple, because there's only the player that is moving around, so the state is just one number, and you can really easily visualize that on top of a grid like this, right? So we were able to write a pretty print function that quickly showed us what the policy looked like. Uh, in case of taxi v3, that is something that we will have to do again. It is not going to be as straightforward as this case, because there are there's a taxi, there's a passenger, and then there are a few other things that are changing. So we need to have a good grasp of how those things are changing, what they are representing, and if you want to debug the taxi problem, then what are those variables that you want to print out, right? So I would encourage everyone, tweak the parameters for the algorithms that we have seen today, then get started with the description, right? If you really want to learn the taxi environment, it shouldn't be all that difficult. The good thing is Google Colab already has it installed. So if you just say import gym, it already has it installed, and then taxi is equal to right? These are basically two lines that you need. Gym has many different environments, so it has this method or this API, which is like a factory. So you specify a string, which is the name of the environment and the version number, and it gives you an object of that environment. And we can test this. Right. Now, of course, you will have to look up the documentation to understand what exactly this is representing, but we are able to render the environment. You can also step through. But yeah, at this point, it becomes really important to really read through the documentation, understand what the actions are, what the states are, how they're being represented, and then after that, once you have that understanding, then it should be fairly easy, because in the end, all you need to do is create a table like this, run many iterations, interact with this environment, and fill up that table, uh, and then test your algorithm by seeing if it is able to. The requirement is that there's a taxi and it has to do a pickup, it has to do a drop off. So then during testing, you have to find out if the pickup is happening correctly or not. Is the taxi taking the shortest route or not? Is it dropping off in the correct location or not? Right. So that is what we need to do. Again, I'll go into more details in our office hours, and I will also introduce the rubrics. But this is the starter code. Make sure you understand everything that we have learned this week, and then you are able to interact with this environment and read through the documentation. Okay. Any questions about the project, about what we did today? Okay. All right. If there are questions, you can always Slack me. I'm happy to answer there as well. I again, again, we are. I think I told this thing yesterday as well, but we are going to a new channel. We are migrating to a new channel on Slack. So you should either be already added to that channel, or you would have received an email to your personal email address, the one you were using for Slack, with a link to do so. So please make sure you are added to the new channel and you're getting the updates, because by, I think, early next week we will have to sort of shut down the existing channel. And I'm already making all the announcements and everything in the new channel. Cool. If there are no questions, I'm going to wrap up. Let me know if there's anything that is confusing or anything. Otherwise, we'll meet on Tuesday for the office hours. We'll lay out the project. We will do a recap, and then, like I mentioned earlier, in week 4 we are going to focus on adding more complexity to the environment. So make it stochastic. We'll make it more dynamic. The players start to move around, and then we will come back and see if the algorithms are still working. Cool. Thank you so much. See you on Tuesday. Bye bye.
Thank you, Farhan. Bye.